Hello, my name is Paul Geyer, and I'm here to chat with you this morning about central heating plant planning. This is what I'll be talking about today, some introductory remarks, policy related to central heating plant planning, and then plant design. Again, this is a discussion of planning considerations, not detailed design. And by way of introduction, just a little bit about me and what I've been doing for the last few decades. This discussion contains data and information as criteria to guide the planning of steam and high temperature water central and individual heating plants. Engineering and economic considerations are identified to guide siting decisions, fuel selection, and the choice of either high temperature water or steam distribution media. The primary purpose of these plants is to generate steam and high temperature water for space heating and process steam in the most economical, operationally efficient, and environmentally acceptable manner possible for distribution to groups of buildings. New heating plants shall be designed to meet application requirements for the lowest overall ownership, operation, and energy consumption cost during their lifespan. The application of any facility must be justified by an economic analysis to ensure the most appropriate facility at the lowest overall cost to the owner. The economic analysis for new or modified plant construction projects shall consider all suitable alternatives to determine the most cost-effective method of accomplishment. Figure 1 provides a list of cost considerations for comparing alternative plants. Plant alternatives, central heating plants. These plants are for groups of buildings which are existing or anticipated within a 5-year program typically. Central heating plants are justified when the distribution system will have a lower life cycle cost than other alternatives. Plants which generate electric power and heat cogeneration can be utilized when an economic analysis determines lower life cycle costs than other alternatives. Individual heating plants are typically inside or adjoin the building they serve. Individual plants are considered when economically justified and for the following reasons: when installation and maintenance of an extension of the distribution system from a central plant to an isolated building is not economically justified, when dispersal of facilities and continuity of services are so essential that disruption of service by any damage to the central heating plant and connecting distribution system cannot be tolerated, and when fuel costs are paid by occupants of residences, as an example. With regard to expansion of existing plants, additional steam capacity, including reserve capacity for loads expected within, say, 5 years, may be added to an existing central heating plant. An economic study must show that modifications and additions to an existing plant and distribution system will be more cost-effective than other alternatives. This is figure 1, which indicates the format for comparing plant costs. This is a continuation of figure 1, which is the format for comparing plant costs. In consideration of rehabilitation versus replacement, if an existing plant has deteriorated to the point of producing numerous outages, is becoming a safety hazard, or is not in compliance with air pollution regulations, its rehabilitation or replacement will be determined by a life cycle economic analysis. If replacement is determined to be the most cost-effective, then the capacity of the modern plant is required to handle any additional projected load. Necessary equipment and systems for air pollution regulation compliance and other operating safety or maintenance deficiencies must be included for either the rehabilitated plant or replacement plant. A standby facility is a facility which is redundant to the primary facility and maintained to operate in the event the primary facility becomes inoperable. A standby facility will be considered only when a crucial need exists and redundant equipment and systems in the primary facility will not provide required or necessary reliability of continuous operation. B, an outage could endanger life or property or seriously interfere with the mission of an activity. C, the financial loss to the owner from a reasonable outage schedule will be greater than the costs of standby equipment. D, the consumer load is sufficiently critical. When a replaced plant is considered for a standby facility, it shall be made suitable for operation in conformance with safety and clean air regulations. In considerations of steam versus high temperature water for a heating plant system, central steam heating plants shall be utilized unless a thorough analysis dictates that a high temperature water plant is preferable. The following factors will be among those considered in the analysis. A, economic advantages of thermal storage of the high temperature water system in sizing of equipment such as boilers, pumps, and piping. B, operating and maintenance cost of high temperature water distribution system versus steam distribution system. C, pressure and temperature requirements provided economically by steam or high temperature water. D, cost of replacement or renovation of existing plant and distribution system compared with construction of new plant and or distribution system. A comparison will be on a life cycle basis. The analysis must indicate a system change is economical before change is made. E, prevalence of skilled plant operators in the area. This is critical in remote locations. The high temperature water system operators require more skill to make the system operate efficiently. And F, complexity of controls and ability of system to maintain fluctuating or constant temperature conditions through the assigned or existing heat transfer equipment. With regard to issues of fuel selection, select fuels which are within the national guidelines and which produce the required performance at lowest life cycle costs. The fuel policy has been to use a solid domestically produced fuel as a primary fuel for heating plants of medium size and above, except where use of a solid fuel is not feasible because of geographic considerations. Existing plants burning fuel oil or gas may continue to burn fuel oil or gas. New or replacement boilers in plants with design input over the threshold minimum established by owner policy are required to burn solid fuel. Another fuel may be used when the primary fuel is not available or where it is critical to keep the steam plant in operation on an emergency basis. When oil is used, the boiler should be capable of conversion to grades number 2 through number 6 oil. It's mandatory to conform to federal, state, and local air and water pollution abatement codes. Where applicable, design shall conform to the industry codes, including the following: ASME Boiler and Pressure Vessel Code, ANSI standards, API standards, National Board of Boiler and Pressure Vessel Inspection Code, ASHRAE, ASTM standards, American Welding Society, American Institute of Plant Engineers, NAPE, NACE, National Association of Corrosion Engineers, NFPA, Air and Waste Management Association, American Institute of Chemical Engineers, and AIME, American Institute of Mining, Metallurgical, and Petroleum Engineers. Now, with regard to planning of the plant design, a plant study shall be conducted before authorization to develop definitive designs. The study will evaluate plant operating parameters with a primary emphasis on economic factors. Major emphasis will also be given to energy conservation and environmental concerns. The documented study shall determine A. Plant load and operating characteristics, B. Fuels to be burned, C. Required dependability of service, D. Predicted lifespan of the plant, E. Estimated cost, both capital and operating, F. Required pollution abatement equipment. Figure 1 provides the predominant costs which affect the plant. It may be used as a basis for comparing plant alternatives. Table 1 provides a list of predominant design considerations for design of thermal plants. Now, with regard to the thermal generating equipment, the combination of number and size of thermal generating equipment in a plant determines the plant capacity. A plant may be installed with a single boiler able to provide the required plant capacity for applications where loss of the boiler will not adversely affect the operation. Most applications cannot tolerate the complete loss of a thermal plant. These applications require that two boilers provide 135 to 150% typically of the plant's maximum steam demand. The continuous capacity of the plant with a boiler not operating shall be greater than the essential plant load. A spare boiler may be needed to provide the necessary backup. The recommended method for selecting the number of boilers in this situation is to use 3 equal capacity boilers which can each carry 50% of the maximum load. A variation of this scheme is to use 2 equal capacity boilers, each capable of providing 2/3 of the maximum load, and a smaller boiler capable of carrying 1/3 of the maximum load. The maximum steam plant demand shall not require operation of more than 3 simultaneously fired boilers. A smaller peaking and off-season boiler should be included if increased efficiency at low loads economically justifies the installation. Avoid installation of initial main boilers whose capabilities are smaller than those to be added when the plant is expanded. Avoid unnecessarily large numbers of small boilers. Table 2 provides design considerations. Factors discussed are load characteristics, fuels, availability of water, electric service, and plant location. With regard to the minimum load for the plant shall operate efficiently at minimum loads. The following variables can be manipulated to meet minimum load requirements. First, the type of fuel and method of combustion. This will determine operating ranges of combustion control turn down, which may range from 8:1 to 3:1. The boiler turn down must include the minimum load. By changing burner tips in oil firing, low minimum loads can be obtained. With regard to the number of boilers, more smaller boilers will lower the minimum plant capacity. This option should not be considered if plant would require more than 4 equal capacity boilers. With regard to the minimum load boiler or boilers, where the difference between a minimum plant steam demand and minimum boiler load with main boilers is large, a small packaged boiler unit with its own boiler feed pumps should be used to provide low plant capacities. Select a plant operating pressure which provides adequate pressure at any user outlet and allows for the pressure drops through piping in the building, distribution system, boiler plant, and the dry piping in the boiler steam drum. Boiler design pressure should be 250 psi minimum for all water tube boiler applications. For all other applications, the design pressure should be determined in accordance with the ASME boiler and pressure vessel code. Modify pressures when it's economical and practicable to distribute steam at pressures below or above those indicated by this discussion. For heating plants normally do not require operating steam pressures over 150 psi-G. Lower pressures have smaller heat losses from distribution piping. Cast iron valves can be used up to 125 psi-G, but steel valves are required between 125 and 150 psi-G unless 250 psi-G class cast iron valves are used. For this reason, the recommended operating pressure range is 100 psig to 125 psig for maximum economy of distribution piping, including valves and fittings. When the maximum plant and distribution loads are large and the most remote terminal requirements cannot be satisfied with sufficient quantities of steam, combinations of higher pressures and related pipe sizes should be analyzed to compare installation and operating costs of various steam pressures up to 250 psig, which is the next higher pressure rating of cast iron valves. For process loads requiring higher pressures than 100 psig, when a process load is required in excess of 100 psig, an economic analysis should determine whether steam should be generated and distributed at the pressure required at the process, distributed at two pressure levels, or generated at the higher pressure locally by a separate heating plant as needed. Water tube and fire tube boilers are the two general types of boilers available. The boilers are also classified as either high pressure or low pressure, and whether they produce hot water or steam. A high pressure boiler is a boiler which operates at pressures above 15 psig. The advantage of the high pressure boiler is reduced boiler size and distribution piping required to equal the capacity of a low pressure boiler. Most large capacity boilers are high pressure boilers. A hot water boiler is a misnomer since the water does not boil. A high temperature water boiler is a hot water boiler which produces water at temperatures higher than 250 degrees Fahrenheit. Other classifications for boilers are type of fuel and method of firing. Burners and stokers are the two general methods of firing, with further categories of these types of firing schemes. Once the operating parameters, load and fuel, have been determined, the type of boilers which will provide the best operating characteristics shall be selected. Table 2 lists the advantages and disadvantages of high temperature hot water boilers versus steam boilers. Table 3 lists acceptable boiler types and criteria to consider when selecting the type and possible pollutants to control. Pollution control equipment will be a major cost factor when evaluating the most cost-effective alternative. Boiler design is primarily dependent on the fuel and type of firing. Both furnace heat release rate and EPRS are factors which determine distribution of heat within the furnace. Proper values must be maintained to keep local absorption to a minimum and avoid hotspots. The primary criteria for design are based on the following. A. Furnace heat release rate. The volumetric heat release rate is the BTU's input rate per cubic foot of furnace volume. B. Effective projected radiant surface, EPRS, the portion of the furnace in square feet which is exposed to radiant heat of the flame. C. Great heat release rate for stoker boilers. Flue gas velocities through tube banks. And E. Tube spacing. Computation of effective radiant heating surface for water tube boilers are based on the following. Bare metal covered or metallic ore covered tubes and headers projected area, external diameter times length of tube, of the tubes or header. B. Extended surfaces, metal and metallic surfaces extending from the tubes or headers. 60% of the flat projected area except that metal blocks not integral with tubes or headers, extended surfaces less than 1/4 inch thick or more than 1 1/4 inches in length, and the part of the extended surface which is more than one tube or header radius from the tube or header from which it extends are not included. C. Furnace exit tubes. The projected areas of these portions of the first two rows of exit tubes receiving radiant heat from the fire. D. Great heat release rate. This burning rate is the higher heating value in the coal used per hour at rated boiler capacity divided by the total active burning area of the stoker grate. These values are based on the assumption that furnace walls are water cooled, that there is adequate furnace volume, and that the most desirable type of coal for the unit is used. In the absence of these conditions, values should be reduced to ensure satisfactory combustion. A high grate heat release rate will cause high carbon loss and increased particulate emissions. E. Flue gas velocities through tube banks. Gas and light oil flue gas velocities are typically determined by the need to limit draft losses. Coal, wood, or solid waste boilers need to limit flue gas velocities to prevent undue erosion of boiler convection tubes. The gas velocities through the convection section of these boilers shall not exceed velocities shown in Table 4. Tube spacing, F. Tube spacing is governed by the amount of deposits which will accumulate. Spacing is not critical for boilers firing gas or distillate oil. Boilers firing solid fuels or residual oil need proper spacing and proper soot blowing arrangement to limit deposit buildup on tubes, poor heat distribution, poor efficiencies, and premature tube failures. Table 4 indicates maximum flue gas velocities in feet per second in convection sections for coal, wood, or solid waste boilers. Now a few comments regarding plant layout. It should be designed to reduce maintenance time and allow for easy operation of equipment. Future situations to consider include A. Tube cleaning, B. Tube replacement, C. Future expansion, and D. Conversion fuels. Tube replacement for fire tube boilers typically requires a space in front of the boiler which is equal to the boiler's longest length. If there is a possibility of future conversion of firing equipment to another fuel, provide space for the installation and operation of such equipment and for local storage and handling of the new fuel. Enough room shall be provided to accommodate all auxiliaries such as feed pumps, fuel pumps, condensate tank water heaters, deaerators, condensate receivers, and other equipment normally located in the boiler room. When steam-driven auxiliaries are used, provide emergency electrical power generation to start up the plant and operate the following essential services until steam pressure is reestablished. A. Coal and ash handling, coal firing, emergency lighting, instrument compressors, combustion management controls, flame safeguard controls, control valves, control room ventilation, and other essential operation requirements, including the auxiliaries for one boiler. B. Emergency electric power shall be provided for all essential services, including plant auxiliaries. Minimum emergency electrical power shall be that which is capable of allowing the plant to generate steam sufficient to serve essential loads. Now, a few comments regarding feedwater pumping systems. The ASME Boiler and Pressure Vessel Code requires that boilers having more than 500 square feet of water heating surface and firing a solid fuel not in suspension be provided with two means of feeding water. It's recommended that all coal stoker fired boilers with a capacity of over 100,000 pounds per hour should have dual feedwater systems containing separate headers, check valves, isolating valves, and regulating valves for operation flexibility and emergency. All coal stoker fired coal boilers 20,000 pounds per hour and above shall have a steam turbine-driven boiler feed pump and a motor-driven boiler feed pump per boiler. Provide the steam turbine boiler feed pump, plant size, with emergency treated water connection for coal stoker fired plants. Consider uses for secondary steam to determine ways to operate a plant more effectively. Several possible ways of using steam for more economical operation are fuel oil tank heating coil, water heaters, absorption type of refrigeration machines, and space heating. With regard to refrigeration units, addition of refrigeration units to a plant design should be considered where heating plant steam can be used during the summer to serve refrigeration machines. Chilled water produced by steam absorption or steam turbine-driven refrigeration compressors can be distributed economically to buildings for space cooling. A combined plant saves considerable building cost. The addition increases annual plant load and may reduce owning and operating cost. Turbine-driven equipment can be economical if there is use for low-pressure exhaust steam. Absorption refrigeration equipment does not work efficiently at low loads. If absorption equipment is not a significant load, it's advisable to utilize electric-driven centrifugal equipment. This eliminates the need for low-pressure summer steam and saves distribution costs, line losses, fuel, and manpower. With regard to the steam-driven auxiliaries, a comparison similar to that outlined in Figure 1 should be made for owning and operating steam turbine versus electric motor-driven rotating equipment. Consider amounts of condensate returned, possible waste of exhaust steam to the atmosphere, and number of operating hours using steam-driven instead of motor-driven equipment. Reliability and continuity of service during power outages should also be factors when determining the most cost-effective alternative. Steam-driven auxiliaries may be provided in lieu of or in conjunction with electric motor-driven units. Possible auxiliaries which can utilize steam drives include feed pumps, condensate pumps, induced draft fans, forced draft fans, air compressors, overfire air fans, and fuel oil pumps. In all cases, sufficient electric motor-driven units must be provided to permit cold startup of the boiler plant. And that brings us to the conclusion of this brief discussion on central heating plant planning. I hope that this has provided you with some useful information, that it was about what you were looking for, and that you will be able to utilize this information moving forward as projects come across your desk in the future. With that, Thank you very much for letting me chat with you, and have a nice rest of the day.